Good morning, everyone. Okay, in the interest of keeping on schedule, we'll start right at 11 o'clock. Good morning, my name is Jeremy Crenshaw, and I'm coming from the University of Delaware, and this is a session on locomotor stability. So again, my name is Jeremy. I'd also like to acknowledge my co-moderators, and I'm wondering if Antonia and Sarah could unmute themselves and introduce themselves briefly.
Hi everyone, I'm Antonia Zaferiou from Stevens Institute of Technology.
I'm Sarah Moudy, and I'm from the University of North Texas Health Science Center.
Great. All right, so we have an exciting lineup of presentations today. Again, the way this will work is we have 3 blocks of 4 presentations. Each presentation is a short 5 minutes. And the reason is then after the 4 presentations, we'll have up to 10 minutes for discussion. And so far in this conference, the discussion has been really engaging. I expect that, so I'm challenging you to make this a very dynamic conversation, and hopefully that spills over into the spatial chat. It looks like we are in S2 Mary, and you can see that there is a link there for that. So I hope to see everyone there. All right, so in the interest of starting on time, I'll ask that Osman Darici from the University of Calgary go ahead and share his screen.
Can you see it?
We can. So go ahead and take it away.
Thank you very much. When human walking is not always on level terrain, humans sometimes walk on uneven terrain, as you see in the below picture. We did a simple experiment and made people walk over a discrete multi-step uneven terrain and recorded their speed fluctuations with inertial measurement units on the feet. And when we look at the speed fluctuations, this you are seeing an example speed fluctuation, speed versus time. These fluctuations look like random noise, but in this talk, I would like to show you these fluctuations are not random. On the contrary, they are anticipatory and deterministic. We can predict this by a simple optimal control model, as well as a simple superposition of one uneven step speed trajectory. Using this, we can predict complex trajectories. For the optimal control model, we will use a simple mechanical model, basically an inverted pendulum-based model. You are seeing an inverted pendulum here with the velocity vector, center of mass vector. When this model takes a step on uneven terrain, it needs to change its actuation because terrain is uneven. And the only actuation that our model has is a push-off impulse, which is a rough approximation of human trailing leg ankle push-off. And when we apply this push-off impulse as actuation, the model is going to redirect its velocity vector, center of mass velocity vector. And then at the end of each model, each step, the model has a collision impulse, which is a rough modeling of human heel strike, which will make the model lose energy. And this impulse is going to make the model again redirect the center of velocity. After this step-to-step transition events, model is going to go for the new step. What we did was we expect for level terrain walking, the push-off work or impulse should be constant and model should have a constant speed because terrain is level. But what we ask model is modulate its push-off while going over an uneven terrain while minimizing total mechanical work or push-off work given speed and distance constraints. Because of the terrain is uneven and model is modulating the push-off work, we expect model will also modulate its speed and figure out the optimal speed and momentum to negotiate the uneven terrain with minimum work. First, we simulated our model over a very simple uneven terrain, just one step up with fixed time and distance. And our model showed us a speed trajectory. This is speed versus steps. And the vertical bar corresponds to the step that is the step up. And as we see here, model has an anticipatory component. It begins to speed up even before stepping up, then losing speed going over the step up, and then regaining speed. This is an optimal solution to negotiate a simple step up. So we will first show, compare this model one-step response with human one-step response if there is any. But we also want to focus on complex uneven terrains such as this one, multi-step. And I'll show you some speed fluctuations of humans on uneven terrains such as this one. And we will ask the model, and our model says its dynamics are approximately linear. So our model says its next speed is a function of the current speed plus terrain disturbance, and of course, actuation or push-off. So our model says one-step response of a single terrain, if we superpose a one-step response of a single terrain, we can generate complex multi-step responses. We will also test this idea on humans and whether we will see we can predict complex human speed responses. To find the human one-step response, we conducted another experiment, a very simple one. Humans basically walked over a simple step up. We record the speed fluctuations. When humans walk over a step up, I'm going to show you speed fluctuations of humans or speed deviations. When I say speed deviations, these are the deviations from average walking speed versus steps, and step 0 or vertical bar again corresponds to stepping up. Here is a test subject average speed. Here is another test subject, and here are 12 test subjects. As we see, while humans walk over a step up, their speeds have a trajectory and they are lining up very well. And the bold red line is the average speed trajectory going over a step up. We can see it better with average speed trajectory and standard deviation. As we see, humans have a similar triphasing pattern as well. Even before stepping up, they are speeding up. Then while going over the step up, they are losing speed, and then they are regaining speed. Model and human speed variations are very similar, and our model is optimal. Here we are showing humans have a one-step response, and it's a structural response. They are overlapping with each other, and our model with optimization can predict it roughly well. Next, I'm gonna go over decomposing a complex terrain because we also want to predict complex terrain responses. A complex terrain is composed of many one-step terrains, and we can decompose it into one-step terrains, and you are seeing some coefficients here. These coefficients are whether the terrain height disturbance is a step up or step down, such as the first two steps are a step up, the second step is another step up, so you are seeing positive coefficients, and the third step is a step down. We can just decompose the terrain into one-step disturbances and find the scaling coefficients based on whether it's a step up or down, also based on the thickness. And we know the one-step response of humans, or also the model, and we can use these one-step responses for each step, each terrain height of the complex terrain. We can scale them with the terrain info and then shift them in time. And if we superpose these responses, it should generate a complex trajectory for us. Basically, what we are doing is we are convolving one-step responses for complex terrain profile to go for the complex response. And if this idea is true, we can go the opposite way. We can deconvolve a complex speed response and then find one-step response. We will test this idea with different terrains. Here I'm showing you 4 different terrains.
About 30 seconds left.
A step down, another complex terrain, and 2 more complex terrain row of the complex terrain that involves multiple ups and downs. Here, green is the measured human speed for a step down, and blue is our predicted speed using the one-step response, scaling and superposition. As we see, humans have the triphasic pattern here, but the pattern is reversed, slow down, speed up, and slow down, unlike the opposite of stepping up. And here you are seeing green human speed responses, measured responses with standard deviation, and in blue our prediction with using one-step response, scaling and superposition. And we have roughly well predictions. You are seeing the correlation coefficients showing how well our predictions match with the measurements. I'm gonna sum up. In this talk, we showed human speed fluctuations on an uneven terrain are not random, and they are anticipatory and deterministic. They have a deterministic phase. Compensations begins earlier than having the uneven terrain. We can have good predictions of these speed trajectories by a simple optimal control model. Mechanical work optimization predict this. And then we can decompose a complex terrain into one-step responses. And then using linearity, superposition, and scaling, basically convolving the terrain info with the one-step response, we can generate complex human speed trajectories. We believe uneven terrain walking is economical and it's simply composable. Thank you.
Wonderful. And as we transition, I'll ask Chuyi to start sharing her screen. Let's combat that awkward lack of applause by liberally using your reaction emojis. I know my kindergartner did some jazz hands in her her online class, so if that's your thing, you can go ahead and do that. So we will ask Chuyi to share her screen now. Osman, if you could stop sharing your screen. And keeping with the theme of changing levels here. Wonderful. Chuyi, if you're ready, go ahead and introduce yourself and begin.
Hi, everyone. I'm Chuyi from Purdue University, and today I'm going to present on vertical ground reaction forces coordination during stair ambulation. So regulation of whole body angular momentum is critical during stair ambulation to prevent falling. It is also known that the whole body angular momentum is regulated more tightly during descent compared to ascent. However, the mechanisms employed under this control are not well understood. The ground reaction forces significantly influence whole body angular momentum during double support phase as shown in the stick figures. The vertical ground reaction forces under the 2 feet could covary negatively, thus stabilizing the vertical acceleration at the central mass. By the negative covariation means that if F1 increases, then F2 will decrease. Therefore, the acceleration here is unchanged. And if a person performed this for multiple trials, we should see the data distribute along the red dot. Conversely, since these ground reaction forces also creating the opposing moment about the central mass, the ground reaction forces could covary positively to stabilize the net moment about central mass, and thereby the rate of change in whole body angular momentum. And if that is the case, we should see data distributed along the blue dots. Therefore, our study is to examine how the vertical ground reaction forces during double support phase are coordinated to regulate whole body angular momentum about the medial lateral axis during stair negotiation. We expect the force sum to be stabilized during ascent and the force difference to be stabilized during descent. 8 young healthy subjects ascended and descended a 5-step staircase and stopped at the top and bottom for 20 times. We quantified the covariation in ground reaction forces for 3 consecutive steps using uncontrolled manifold analysis. To do that, we partitioned the cross-trial force variances into a component along the uncontrolled manifold that maintains the sum of the 2 forces and the component that is orthogonal to it. The synergy index was computed as the normalized difference between the 2 variance components. A synergy index greater than 0 means that the force sum is stabilized. Conversely, a synergy index smaller than 0 indicates that some moment about central mass is stabilized. We found the synergy index greater than 0 for all 3 steps during stair ascent, like shown in the black bars, meaning that the vertical forces are covarying negatively to stabilize the force sum, which supports our hypothesis for stair ascent. In contrast, the synergy index for stair descent declines progressively for each step and is not different from 0 at the bottom step, which is over here. Overall, we conclude that the synergy index is lower during descent compared to ascent. This indicates there is a shift towards regulation of whole body angular momentum while descending compared to ascending stairs. Furthermore, this shift occurred after descending the middle step, and that could be because whole body angular momentum tends to increase while descending multiple steps as the body rotates forward about the ankle at each step. The decline in synergy may be a compensatory mechanism to regulate the increase in whole body angular momentum. An alternative interpretation is that the decline in synergy may be preparation for transitioning the body from descending gait to quiet standing at the bottom, which almost requires 0 whole body angular momentum here. And recall our definition that the stabilization of the moment is indicated by a negative synergy index. Although the synergy index was never less than 0 significantly in our data, we cannot conclude that the net moment was not stabilized. And that is because there exist ground reaction forces in anterior posterior directions under the 2 feet also that would contribute to the moment above central mass. And those were not considered in our current analysis. However, we can conclude the prioritization of stabilization for the moment from the decline in synergies about the sum force. In the future, we would like to include ground reaction forces in all directions to characterize the stabilization of net force and moment during stair negotiation, and establish whether the synergy metrics are valid predictors of falls on stairs. We also expect that our results to be useful in design and control of powered lower limb prosthesis for stair ambulation. Thank you.
Great, thank you. And I'll ask Kaitlyn to go ahead and share her screen. As a reminder, if you have questions, please do put those in the chat so that we can address those during our question and answer period. With that, from the very prestigious University of Delaware, we have Kaitlyn Downer. Go ahead, and Kaitlyn, and take it away.
Thank you. My name is Kaitlyn Downer. I'm going into my senior year as an undergraduate in mechanical engineering at the University of Delaware. Today, I'm going to present our work on determining the effect of center of mass on adaptive treadmill control. Treadmill training is a beneficial rehabilitation tool for neuromuscular disorders that impact gait, such as stroke and Parkinson's, as it is low cost and allows for repetition of movement in a small space. Compared to fixed speed treadmills, adaptive treadmills provide a more similar environment to overground gait due to variability. This allows for changes in speed in real time due to the natural gait mechanics. However, most current adaptive treadmill controllers base real-time speed off of position and spatiotemporal parameters only and do not consider propulsion, which is known to have a strong positive correlation with walking speed. Our lab developed a novel adaptive treadmill that adjusts belt speed based on real-time changes in user bilateral step length, bilateral propulsive impulse, and center of mass position relative to the treadmill center. Each of these terms are weighted, and the coefficients alpha, gamma, and beta dictate the importance of step length, propulsive impulse, and center of mass position, respectively, on determining the overall belt speed. In this study, we wanted to determine the impact of the center of mass position term on users' gait mechanics and overall comfort and stability. This was accomplished by adjusting beta, the weight on the center of mass position term. The original beta term used in previous studies, along with 3 modifications of beta, were tested. 22 young, healthy adults walked on each of the 4 conditions for 1 minute each, and motion capture and ground reaction force data was collected. We asked the question, how does modifying the importance of the center of mass position term impact a user's step length, propulsion, and stability? The figure shows the group average and standard deviations of step length for each modifications of beta. From left to right, you see the increasing order of the magnitude of beta. No significant differences were found in step length between any of the modifications. Moving on to the ground reaction force results, the first group in this plot shows anterior ground reaction force impulse. The second group shows posterior ground reaction force impulse, and the third group net impulse across all 4 conditions. Again, each bar represents the group average plus or minus 1 standard deviation, and from left to right in each group, data is shown in increasing magnitude of beta. The important result here is that the net impulse significantly increased from very small beta to large beta. In other words, participants shifted their net impulse closer to 0 as the weight on the center of mass position term is decreased, suggesting that a smaller weight on position may target increased propulsion without causing changes to gait mechanics and or the spatiotemporal parameters. Finally, participants were asked to rank their stability and comfort on a scale from 1 to 7, with 1 being very unstable or uncomfortable, and 7 being very stable or comfortable. There were no significant differences in both stability and comfort across all modifications of beta. As the net impulse was increased, participants still felt stable and comfortable. In the original adaptive treadmill controller, the center of mass term was included for a safety factor, so that when you moved towards the back of the treadmill, it would slow down. Since participants did not feel unstable or uncomfortable when the beta term went towards 0, the center of mass term may be able to be minimized or removed without a change in security. In this study, participants shifted closer to a net 0 ground reaction force impulse as the weight on beta was reduced. These results suggest that the significant difference in net impulse may be due to the decrease of weight on the center of mass position. From this, adaptive treadmill controllers can be designed to increase net propulsion by decreasing the importance of the center of mass position. Thank you, and I look forward to answering any questions that you may have.
Great, thank you. And as we transition, Paul, please share your screen. Again, please put your questions in the chat. Liberally use our applause emoji. And now I'd like to introduce Pawel Golyski from the Georgia Institute of Technology.
Hello, everyone. Can you all see my slides? Hello?
Yeah, we're good.
All right, great. Hello, everyone. My name is Pawel Golyski, and today I'll be presenting my work entitled "Which Joints Compensate for Destabilizing Energy During Walking?" Previous work by Taylor, Dick, and colleagues demonstrated the ankle and plantar flexor muscles play a major role in dissipating the mechanical work of a perturbation. In the pie charts, we can see that as an individual experiences a rapid drop in ground height during hopping, the change in potential energy at the center of mass to transition between the elevated and ground level steady state conditions is mediated by increased overall negative leg work, which is the size of the pie on hop P, and 3/4 of that negative leg work is contributed by the ankle, shown as the blue section of the pie. Based on this behavior, we hypothesized that the ankle joint will also compensate most for destabilizing energy during walking. To address this hypothesis, we leveraged the fact that split belt treadmills can be used as energetic tools. Specifically, since during treadmill walking, the legs perform mechanical work on the moving treadmill belts, by changing belt speeds, we can alter the mechanical energetics of the legs. For our experiment, we exploited this idea by targeting transient increases in belt velocity to early or late stance. Here we can see an example of a late stance perturbation in real time and then slowed down. Keep an eye on the right leg. And here it comes slowed down. So we collected N = 7 young, healthy individuals with 222 perturbations total. As we can see from the plots on the right, our perturbations occurred between 10 and 45% of the gait cycle for early stance onsets, and between 30 and 65% of the gait cycle for late stance onsets. Although our perturbations were designed to alter the flow of energy between the limb and the treadmill, this is only one part of the leg's energetic story, which is also composed of the energy flowing from the leg to the center of mass and the peripheral work of the leg segments relative to the center of mass. Only by summing all of these contributions can we calculate a corrected leg power, which is shown here averaged across our participants over unperturbed gait cycles. This corrected leg power should be approximately equal to the sum of the ankle, knee, and hip powers calculated from inverse dynamics, which we can see was the case in our unperturbed trials if we compare the joint sum in black with the corrected leg power now shown in red. Through our perturbations, we extended this idea to investigate how the ankle, knee, and hip joint contributions change to mediate the changes in work of the legs during and after the perturbation. Again, we calculated the corrected leg powers as the sum of the treadmill, center of mass, and peripheral contributions, with that being visualized on the left over perturbed gait cycles. For these perturbed strides, we can see that there are substantial changes in mechanical power across all joints on the right, relative to the steady state power fluctuations shown in black. By integrating leg and joint powers and regressing changes in individual joint work with the changes in corrected leg work and calculating R² values across all 222 perturbations, we identified which joints best reflected the changes in demand of their respective legs. We found that changes in joint work were best correlated with changes in leg work at specific joints on the perturbed stride and the first recovery stride. On the perturbed stride, ipsilateral ankle and contralateral knee work best reflected changes in respective leg works. The data used to generate those R² values can be shown on the right, with corrected leg work on the x-axis and joint work on the y-axis. We can see that the perturbations were able to elicit a diverse range of work demands on the legs by looking at the spread along the x-axis. Using the same analysis, we found that on the first stride, changes in both ipsilateral ankle and hip work reflected changes in corrected leg work. So in summary, we found that different onset timings of belt accelerations could elicit a range of mechanical demands on both legs over multiple strides, and that changes in leg work during the perturbation are best reflected by changes in ipsilateral ankle work, with the contralateral knee reflecting an initial response, followed by a response at the ankle and hip. Thank you to my PI, lab mates, volunteers, and funding sources, and I look forward to your questions.
Thank you. And you can unshare your screen. And before I turn it over to Antonia for questions, we have a few minutes for that. I do want to point out, as the discussion spills over into Spatial Chat, you can do things like temporarily share images and videos to help facilitate those discussions. So I do encourage you to do that. So Antonia, are you ready with questions?
Sure. I have questions for each presenter. For Osman from Satya, very nice approach. How would you alter your model to incorporate age-related changes?
Sorry, I'm not seeing the question. Could you?
I'll put it in the chat.
Sure.
How would you alter your model to incorporate age-related changes?
Okay, that's a thing we haven't thought of before, but for age-related changes, maybe balance might be an issue. And our model is basically focuses on mechanical work optimization rather than keeping the body state or balance or controlling the limbs, because it's too simple. Maybe I think to accommodate age-related changes is simulating a slightly more complex model with some state estimation, like some feedback from the states. So a controller, a high-level controller might find the overall speed changes, optimal speed to negotiate uneven terrain, while another low-level controller can go for state estimation of the model. And for age-related stuff with age, maybe the state estimation might be more difficult because of sensor noise. Same experiment with a more complex model, I will say shortly, might accommodate the changes, and then this might make the speed trajectory slightly different or more difficult to achieve. Some noise, adding some noise to the model, basically.
Thank you very much, Osman. For our next speaker, Chuyi from Younghee Chang, thank you for the nice talk. I'm curious if you saw greater variability in individual ground reaction forces on the bottom during descent. Could outliers in ground reaction forces, for example, due to impact forces, potentially be overweighting the non-goal equivalent variant?
Well, thank you for the question. So we do have the variance in each forces calculated, but I don't have it on top of my mind whether it is greater at the bottom step. So usually we'll plot so in our data analysis procedure, we usually plot all trials from 20, all time series from 20 trials and see if there's outliers. However, we don't have a fixed criteria of, so we usually don't exclude any trial because it's has a little bigger magnitude in forces in our procedure right now. But we would love to hear more about whether we should exclude certain trials out of it. But it is possible that I can imagine the forces being the forces being like the impact forces may happen during bottom steps. And hope to chat with you more afterwards.
Thank you very much, Chuyi. For Kaitlyn from Sydney Bodden Distel, great job presenting. It looks like the means of values for your values are stable regardless of changes in beta, but the standard deviation does look like there might be something there as beta changes. Have you considered this or looked into variability differences of measures?
Yeah. So the standard deviation, especially in the step length, was something that we are looking into. We did ask participants other survey questions that include how easy or difficult was it to achieve and maintain their speed. And we found that as beta was decreased, they found it more difficult to achieve and maintain, even though they still felt the same comfort and stability. And we believe that the large standard deviation was due to the different ways that the users would achieve their desired walking speed. And it is important to note that the walking speed was not significantly different across all conditions. So it was more on a different individual basis that led to that.
Thank you very much, Kaitlyn. And finally, for Paul from Satya, did you look at coordination between the joint works? Would they co-vary to stabilize network?
Thanks for the question, Satya. I did not look at that directly. What we did is there was like a coarse version of that by looking over the entire stride, how changes in work changed with overall leg work. However, I think it's an interesting approach because what you could see if you looked at it as a time series comparison of power fluctuations, if you added up all of the joints, they should directly co-vary with overall leg power. But it could be that a single joint drives the response and then two of the other joints are basically opposite of one another. So they could almost cancel each other out. So I think that would be a really cool way of looking at it differently. Yeah.
Thank you very much. Thank you to all the speakers and participants for the questions and thoughtful answers. Jeremy, I don't know if you want to say a few words, but we're right on time to start the next block of
I have no desire to say anything.
Of talks. Okay, well, thank you all again for really kicking off this session in such a dynamic way. So let's turn it over to our tech support for a pre-recorded video from Andrew Dragunas, body weight support disrupt stepping coordination.
Good afternoon, everyone. Today I'll be describing my work evaluating how bodyweight support devices affect stepping coordination. Bodyweight support is a common rehabilitation tool that can successfully improve walking speed and endurance for people with neuromuscular deficits. However, these systems have had limited effects on improving lateral balance. The maintenance of lateral stability is a requirement for independent walking, and walking interventions such as bodyweight support should encourage individuals to adopt an appropriate stepping strategy to carry over to real-world walking. Bodyweight support has complex effects on gait, as the force exerted by bodyweight support is not evenly applied to the body. As the force of the bodyweight support system is applied through a trunk harness, bodyweight support will change the inertial behavior of the trunk, but not the lower extremities. Bodyweight support also changes the normal spatiotemporal features of gait and the normal kinematic trajectories, which will change the relationship between the center of mass and the swing foot during the gait cycle. We hypothesized that bodyweight support would reduce coordination between the lateral center of mass state and lateral foot placement, and that this effect would scale with the level of bodyweight support. We recruited 9 healthy young adults and had them perform 2 minutes of treadmill walking at 3 levels of bodyweight support, 0%, 30%, and 60%. We measured the dynamics of center mass and foot placement through several metrics. Our primary outcome measure was the correlation between lateral center of mass state and lateral foot placement position during the swing phase. This was represented as a time series R² value. We also measured symmetry of the center of mass in the transverse plane by parameterizing the center of mass trajectory and computing a symmetry index. And lastly, we also measured lateral foot placement position relative to the center of mass position. So when walking without bodyweight support, lateral center mass state became increasingly predictive of lateral foot placement position. At the beginning of swing phase, 55% of the variability in foot placement can be explained by variability in center mass state. This increases to 80% by the end of swing. At 30% bodyweight support, we see reductions in the R² time series trajectory, and the trajectory at 30% bodyweight support is significantly different from that without bodyweight support. This trend continues as we increase bodyweight support to 60%, where only 50% of variability in foot placement can be explained by variability in center mass state at the end of swing phase. The R² time series trajectory at 60% was significantly different than at 0 or 30. So as bodyweight support increased, stepping coordination progressively decreased. This may reflect a stabilizing effect of bodyweight support, where the demands to maintain lateral stability are reduced as the percentage of bodyweight support is increased. When walking without bodyweight support, there was relatively good symmetry between the left and right sides of the body. At 30% bodyweight support, the center of mass trajectory became slightly biased towards the right side of the body, but there were no significant differences in symmetry between 0% and 30% bodyweight support. However, at 60%, we see a substantial bias towards the right side of the body, and there are significant differences in transverse symmetry between 60% body weight support and both 0 and 30%. So as body weight support increased, the center of mass trajectory became increasingly asymmetric, and high levels of body weight support produced center mass dynamics that did not replicate the dynamics of real-world walking. We found a similar right-left asymmetry in foot placement position. As body weight support increased, the right leg was placed more lateral to the center of mass, and the right foot placement at 30% body weight support was significantly more lateral than at 0%. And similarly, the right foot placement at 60% body weight support was more lateral than at 0 or 30%. And we see the opposite occurred on the left leg, which was placed more medial to the center mass as body weight support increased. Left foot placement at 30% body weight support was more medial than at 0%, and likewise for 60% body weight support, which is more medial than 0% body weight support. So this asymmetry in foot placement may be reflective of a compensatory stepping strategy at high levels of body weight support. So in conclusion, we found that as body weight support increased, coordination between lateral center mass state and lateral foot placement decreased. Body weight support also produced asymmetries in center of mass trajectory and lateral foot placement position. And body weight support may encourage a stepping strategy that has limited translations to the controlling frontal plane center mass dynamics during real world walking. I'd like to thank my funding sources for allowing me to complete this work. And should you have any questions, I can be reached by email below. Thank you.
Okay, our next presenter is Daisey Vega from University of Houston, who will present stepping kinematics indicate minimal disruptions to balance control when linking the arms and legs during treadmill walking.
All right, sorry about that. I was trying to find the mute button. All righty. Can everyone see my screen? Awesome. All right. Good morning, everyone. My name is Daisey Vega. I'm a PhD student at the University of Houston, working with Chris Arellano. And this study was done in collaboration with Dr. Helen Huang. So if you went to ASB last year, you probably saw my talk where I talked about this fun little experiment where we connect the arms to the legs. And what we found was that when you have this system, it assisted with forward propulsion and it reduced metabolic power by 17%. So, okay, we saw a mechanical and energetic benefit, but we kind of wanted to have a follow-up analysis on this because we think another important factor to consider is balance, especially if we want to translate this potentially in a gait rehabilitation setting. We don't want to cause any more disruption to someone who already might have poor balance control, right? That might lead to falls and injury, hinder walking recovery. So we asked this question, well, was balance disrupted when physically linking the arms and the legs? And the way we quantified balance is we use stepping kinematic variability. Why? It's just a simple metric of walking balance. It has good validity for predicting fall probability, and it could be easily quantified in a clinical setting and has been done so in those with a spinal cord injury. And specifically what we used was step width, step length, and step time variability. So if our system did disrupt balance, which we think might have due to a lot of like shoulder protraction, then we would expect an increase in the variability of at least one of these stepping parameters, increased variability being a reflection of poor balance. And as a secondary aim, we also wanted to investigate any potential changes in their foot placement strategy, which may or may not be coupled with this increase in variability. And so we took the data from this previous study where we had subjects walk with this device, and we call that assisted walking, and without the device, and we call that normal walking. And from that data, we took the positions of the heel marker from step to step, and we quantified step width, step length, and step time. And we did that over a series of 288 steps for all subjects. And so what we found in terms of their stepping strategy, out of all three parameters, subjects increased their average step width. Now I'll come back to this. So let's take a look at their walking balance. Their step width variability, there was no increase. So what does that mean if we saw an increase in their average step width? Well, we think what might have happened was probably just a fault in the design of the system. Maybe the pulleys were just too wide for subjects, and that's why they had to adopt a wider step. But because there was no increase in their variability, then we interpret that to say, okay, they adopted a wider step, but they were in a lateral direction. And then for their step length variability, there was no increase. So we said, okay, they were able to maintain appropriate balance in the anterior posterior direction. And in terms of their temporal component, there was a statistically significant increase in their step time variability. So we saw that they adopted wider steps and there was disruptions to the temporal component of their walking balance. But to what extent was that really disrupted? How meaningful was it? So we kind of looked to the effect size to kind of compare that to data out in the literature. And we kind of took this broad range approach with disorders that cause balance deficits in older adults who experience multiple falls. And if you take this range of effect sizes and you compare it to ours, which is 0.012, the effect size is 124 to 34-fold smaller. And so we interpret this to suggest that the disruption was minimal. So overall, minimal disruption in walking balance when linking the arms and legs in healthy subjects. Now, in previous, it's healthy subjects, right? So before we can think about potentially applying this in clinical populations, right, we don't know if this minimal disruption might end up being major. So we might want to go back, rethink the design of the system, if we can come out where we can still use the arms and have a mechanical and energetic benefit without really affecting the stepping parameters. All right, and that's all what I have. If you want more information in terms of our previous study or lab links, please scan this QR code. All right, I'll stop my screen.
Thank you very much, Daisy.
Hmm?
I'll try to hit the emoji for clapping here. Okay. Our next speaker is Charisse Hill from Clemson University MUSC, Sex and Race Differences in Center of Pressure Trajectories During Shod Gait.
All right, thank you so much for that intro. Let's see if I can get this shared correctly. Can you guys see my screen okay?
Yes.
Good. Okay, great. So thank you again for that intro. Again, my name is Cherice Hill.
We are not seeing the actual presentation mode. That's the only thing.
Sorry about that.
Okay.
I do not think that my computer liked that I had two monitors set up.
There you go. There you go. Cool. Okay, Charisse, take it away.
Thanks so much for that introduction again, and thank you all for coming to this session. Again, my name is Charisse Hill, and I'll jump right on in. So progression of the center of pressure, or COP, is essential for normal locomotion, and we know that COP trajectories describe functional foot behavior, movement performance and efficiency, and balance and stability control. While normal COP motion has been fairly well defined, particularly in middle-aged and older populations, sex and race COP trajectory differences in healthy young adults have not been previously reported. And this information is also really important in order for us to characterize our very diverse general population, and given disparities both by sex and race in balance and stability related outcomes such as fall risk. So the purpose of this study was to test the hypothesis that COP trajectories during gait would differ between sexes and racial groups in young adults. So we recruited 92 participants with the data set equally divided by sex and race. And we gathered force plate data during 7 shod walking trials at 1.35 meters per second. And we looked at both discrete and continuous outcome measures. So discretely, we looked at initial and final proximal distal COP location, along with total proximal distal excursion. And we also looked at peak lateral and medial location, shown here in figure 1 on the left. And to analyze those discrete measures, we used a multivariate ANOVA and partial eta squared effect sizes. We also wanted to look at the entire COP trajectory instead of only those discrete points. So we looked at the proximal distal and medial lateral COP trajectories continuously using the same method previously described by Pataki, utilizing statistical parametric mapping, and specifically a paired Hotelling's t-squared test, looking at both the proximal distal and medial lateral components together, and then post hoc SPM tests looking at each component separately. So discretely, we found that only sex was significant in our MANOVA. So we focused on the sex effect for the 3 variables that were significant within that MANOVA, which were initial and final COP location and proximal distal excursion. And we found that, again, COP trajectory began more proximally and ended more distally in females, leading to a greater COP excursion in females, as shown here in table 1. And we did find medium to large effect sizes for each of those discrete measures. And then we continued on to look at the continuous data. And here shown in the figure on the right side, figure 3, you can see all of the sex differences shown on the left-hand side of the figure and all of the racial differences shown on the right side. So at the top, we've shown the paired Hotelling's T-square test, which again takes into account both COP components. And you can see that we found a sex difference throughout late stance and a racial difference very early in early stance. Looking specifically at each of the components, focusing on the medial-lateral component, we didn't find any sex differences, but we did find racial differences in medial-lateral COP trajectory during early stance. And then it was the reverse when we looked at the proximal distal data with sex differences throughout late stance and no racial differences. And this is just another visualization of that same data, just so that you can see the actual data traces in a little bit more detail. And again, when we look at sex, we see the divergence in the proximal distal data during late stance. And when we look at the racial side, we see a divergence during early stance and medial-lateral COP trajectory. So why do we think all this is important? COP trajectories can go into informing risk analysis, intervention planning, and rehab protocol development. So understanding sex and race differences and being able to have a really diverse data set to contribute to those analyses and planning protocol developments is really important for both research and clinical care. And in kind of understanding and teasing deeper into why we might have seen these differences, it was really interesting for us to find pieces of previous literature that may contribute. So for example, COP excursion was found to be smaller in middle-aged and older women compared to men. But our study actually found the opposite, where we found larger COP excursion in young adults and young females compared to young males. We also found that a previous study had observed a smaller foot length to overall height ratio in females compared to males, which made us think that perhaps there's a different utilization of COP excursion by sex, with females perhaps utilizing a larger degree of their total excursion or of their total foot length during gait because they have a smaller foot length to overall height ratio. So these would be really interesting things to look at further in the future. And the racial differences that we observed from the study may be related to racial disparities in fall risk or other chronic conditions, and could be explained by foot type or foot flexibility, as pes planus is more common in African Americans than white Americans. And again, that would be a really interesting thing to look further in the future. This study, as many others, has opened up the opportunity for a lot more really interesting analyses. And with that, I'd like to acknowledge all of the collaborators on this project and all of our funding sources. And thank you all so much for listening. I look forward to any questions.
Thank you very much, Charisse, for this important work. Our next speaker is Jennifer Leestma from Georgia Institute of Technology. Perturbation direction reverses the effect of timing on peak center of mass speed.
Sorry, give me one sec. All right, are you able to see my screen okay?
Yes.
Okay, great. So thank you so much. My name is Jenny Leestma, and today I'm going to be talking about some of our work looking at how perturbation direction and timing affect peak center of mass speed. So to jump right in, our research question is, how do individuals maintain stability following diverse perturbations? And some of the characteristics of perturbations that we're looking to investigate are magnitude, direction, and timing. So for this specific analysis, we're going to be investigating the hypothesis that perturbations beginning earlier in stance phase, so the longest amount of time until the next heel contact, will be the most destabilizing regardless of perturbation direction. So to do this, we're using a diverse perturbation set that we collected in our lab that first varied magnitude and direction using translational platform slides. So using this, we are able to perturb the platform in the mediolateral, anteroposterior, and diagonal directions. And we're perturbing to overall distances of 5, 10, and 15 centimeters, making up our different magnitudes. Additionally, we tested perturbation timing, where we targeted a perturbation onset time of 50% of double stance, as well as 25, 50, and 75% of single stance. And the histograms shown here are for a single subject, just showing that we were able to kind of get those perturbations to onset during our desired onset times. So to provide just a little bit more context, here's a quick video of what one of these perturbations looks like. And what this kind of feels like is you're pulling the rug out from under someone. So just to kind of orient you a little bit, if you pull the rug out, the platform slides to the right of the person. That typically results in a leftward pitch of their center of mass. So to address this hypothesis, we're kind of zooming in on the direction and timing variables of this study, where direction, we're lumping together all medial perturbations shown in the cooler colors and all lateral perturbations shown in the warmer colors. And we're looking at these across all 4 perturbation onset timings that I just mentioned. And to start in this analysis, we're just kind of looking at a simple metric, which is peak medial lateral center of mass speed, and specifically looking at the medial lateral direction, because with the medial or lateral perturbation, that's the center of mass component that we expect to change the most. So to find this metric, we're looking at the medial lateral center of mass velocity during the trial, and we expect to see some sort of natural oscillation leading up to the perturbation while they're in steady state. But following the perturbation, we expect to see some sort of deviation in the center of mass trajectory. And then we're looking at the kind of absolute value or overall magnitude of these peaks and taking the peak center of mass speed at any point following the perturbation, just to get some insight into what was the peak instability at any time after that perturbation occurred. And then to normalize this across subjects, we normalize everything to the Froude number, which takes into account the subject's leg length. So the results that I'm going to be showing today are for 4 subjects, which is 864 perturbations. And what you're going to see on the x-axis here is our 4 timing conditions. So the double stance and single stance percentages that I mentioned earlier. And on the y-axis, you're going to see the peak center of mass speed. And just to kind of give a reference point, this black bar here is for steady state walking and the peak center of mass speeds that we saw during those components of the trial. So to start out with lateral perturbations, which again are perturbations that are kind of going to induce a widening step as a response, we can see that the 50% double stance perturbation results in higher peak center of mass speeds in comparison to steady state and the other timing conditions. And those peak center of mass speeds get lower during the single stance portion of the perturbation onset times. However, when we look at medial perturbations, which again are inducing a narrowing step or sometimes a crossover step, we can see that this trend essentially reverses. So the 50% double stance time is the lowest of all perturbation onset timings, whereas the peak center of mass speed tends to get higher and higher later in single stance phase. And just as kind of a reminder, our hypothesis was that there would be no interaction between timing and the direction of the perturbation, and we were expecting both 50% double stance across both types of perturbation trials to be the most destabilizing or show the highest peak center of mass speed. A brief kind of insight into why we think this might be has to do with kind of the tolerance and the ability to perform a widening step maneuver in comparison to a narrower step. And I'd be happy to chat more about that in the question period or in spatial chat after. So the main takeaway from this study is that multiple variables are interacting to affect biomechanical stability. And our future work is aiming to understand the interaction of all 3 of these variables. So also incorporating that magnitude variable and understanding the interaction between all 3. And in the future, we're also planning to evaluate this data using more thorough balance metrics, such as whole body angular momentum. In the future, I think this work has the potential to drive therapy strategies and clinical outcomes, inform bio-inspired control strategies for bipedal robots. And my specific direction for the remainder of my PhD is going to be developing wearable robots to augment stability in impaired populations. I'd like to thank my lab, my PIs, and my funding sources, and I'd be happy to take any questions.
Thank you very much, Jenny. And I'll turn it over to my colleague, Sarah, for questions.
Everyone, great job on all those presentations. So we'll start with just one question for each of the presenters. And then if we have some more time, we can go on to some additional questions. So I believe Keith Gordon, who was the co-author on Andrew Dragunas' presentation, he's here to answer those questions. So Ajit asked, was it always favoring the right, or was there any way to make it go to the left limb instead? Did that agree with the dominant leg?
Yeah, so the asymmetries that Andrew identified with increased body weight support were consistently in the same direction across all our participants. All our participants, yeah, we need to refer back to Andrew. I believe they were all right leg dominant, but I would need to double check on that.
Great. So for Daisey Vega, we have a question from Antonia. What was the familiarization period like? Is it possible that these results are transient responses to learning to walk with a new device, such as widening base support during learning protectively?
Yep, that could be a possibility. The familiarization period was just 2 to 3 minutes. That was just to make sure they were actually able to walk at 1.25 meters per second while they were linked with their arms to the legs. So that might be it. Like another reason why they might have adopted a wider step. Yeah, they might have been more cautious, probably that fear of falling, even though they had a harness on. So definitely for the future, we might need to add a longer training period and see how the stepping changes over time.
So for Charisse, we have a question from Sam, who said, nice presentation. Were the participants wearing their own shoes? I would suspect that shoe differences might affect COP trajectory.
Yes, so I apologize for forgetting to mention that, but yes, everyone came in and wore the same spandex, the same shoes, our lab set, Nike Pegasus Zoom. Again, I completely agree that that would have certainly impacted the COP trajectories that we looked at with shot walking. So yes, shoes were normalized.
And then we have for Jennifer, we have a question from James, who asked, what was the approximate timing of the peak center mass velocity relative to the timing of treadmill displacement? Do you think that there is a reactive component to the observed changes in peak velocity, or are there differences due to passive dynamics?
Yeah, absolutely. So for this specific analysis, we didn't look at the exact time of the peak center of mass speed following the perturbation. We were just kind of looking at, at any time following the perturbation, what would be the peak. And part of the reason I think it's been hard to kind of nail in on exactly when to sample that is since we are varying the perturbations in time, it can be hard to take kind of a standard one after where you'd expect all the perturbations to kind of have the same effect. But one of the approaches we thought about taking is kind of normalizing everything to either percent gait cycle or a similar metric and looking at the deviations in comparison to steady state. So the deviation of the perturbed trajectory. And then to answer your second question, yes, I think there's a lot of complexity in here with the passive dynamics versus the active response, and something that we're thinking a lot about and trying to kind of parse out the different recovery strategies that we're seeing. So yes, I think there is definitely a passive dynamic response as a result of the perturbation. Specifically, I think in the widening step, it's the most intuitive to think about. But just like an anecdote for the other type of perturbation that induces a crossover step, one of the things that we are seeing is either because of the person's active strategy or the passive dynamic response. When you perturb them in double stance and their swing leg comes in as trying to cross over, we've actually had quite a few swing leg with stance leg collisions. So there might actually be some passive dynamics that the person is having to avoid using active control to combat some of these perturbations.
Wonderful, thank you. I think we have enough time to ask another couple questions, so I'm going to go ahead and do that. I'll go back up to Andrew's presentation for questions for Keith. We have another question from Satya, who asked, does the shift in center of mass dynamics reflect difference in leg strength or maybe some asymmetry in the harness itself? Did you calibrate the harness to see if it supported the body in a symmetrical way?
I think there's a, yeah, as we were looking at it again, we were surprised by the findings that we saw with asymmetries. There's a possibility that it could be related to the harness. We had an overhead support system on a trolley that would allow movement left or right, and the trolley was actually aligned perpendicular with our treadmill. So if there was asymmetries in the movement along the treadmill, it's possible it could have had interaction. These are things that we want to look into a little bit further in the future to try and identify where and what are the causes of those asymmetries if they're not related to the neural control itself. Choosing one limb to be supported in conditions of greater body weight support, for example. Thanks.
Great. Okay, I think that's all the time that we have for questions right now. But just another reminder, there's a follow-up discussions can happen in the spatial chat room S2 Mary. There's a link in the chat for that as well. And then Antonia just added back in. So please ask any questions of any of these authors in that chat room. Okay, so for our final block, we will go ahead and get started. Our first presenter is Mitchell Tillman from Stevens Institute of Technology, who will be presenting their research on frontal plane whole body angular momentum during pre-planned and late queue turns.
Okay, everybody can see my screen?
Yep.
Beautiful. Okay, thank you for the introduction. So up to half of walking steps are turns, requiring changes in linear and angular momenta while maintaining balance. Balance is facilitated when the center of mass is directly above and within the base of support, with forces producing a net zero moment about the center of mass. In contrast, turns are facilitated when forces acting at a distance away from the center of mass generate a net moment about the center of mass in the transverse plane. And these mechanical objectives conflict during single limb support. Many times we're able to fully pre-plan our turns, and even these turns increase angular momentum relative to straight line gait. However, if the cue to turn is provided suddenly, previous studies have found increases in center of mass acceleration and ground reaction force magnitudes, suggesting that late cues to turn may challenge balance. And we're interested in understanding how a late visual cue to turn affects whole body regulation of angular momentum, such as when a grocery sign in a grocery store comes into view. We asked 10 participants to perform straight line gait, pre-planned turns, and late cue turns to the left. During these tasks, we asked them to pretend that they were in a grocery store, but that they were not in a rush. In the late queue turns, we told them that there was a 50% chance that the grocery item of interest was in the aisle, and if it was not, there was a visual cue for them to continue walking straight down the 10-meter walkway. Although we're interested in all three directions of angular momenta, here we analyze frontal plane whole body angular momenta about a vector aligned with the pelvis's anterior axis. We compared the range of the frontal plane angular momenta during the turn phase or during straight line gait. Turn phases were defined by the heel strikes before and after onset and termination of pelvis rotation, with a threshold defined per participant as 3 times the standard deviation of straight line pelvis heading angles. On this plot, we'll see the min, max, and range for angular momenta for straight line gait in black, pre-planned turns in purple, and late cue turns in blue for all participants. Each subject had a significantly larger range in at least one of the following comparisons: pre-planned versus late cued, straight line gait versus pre-planned, or straight line gait versus late cued. Participant 5 demonstrated a non-significant smaller range during late cue turns that we're still investigating. Other observations include that there were larger variability in late cued versus pre-planned turns, and that most of the difference in range was driven by differences in minima that generally showed that late cued turns often used more angular momenta that would rotate the body above the center of mass towards the left in the direction of the turn. In summary, all participants used a significantly larger range of frontal plane angular momenta during late cued versus pre-planned turns or during turns versus straight line gait. To provide some context for these findings, we also found slower approach speeds during turns and that late cue turns were shorter duration with fewer footfalls versus pre-planned turns. We're currently exploring the effect of turn strategies on balance. Traditionally, turns have 3 steps: an initiation, continuation, and termination step. However, our turn phases included varying numbers of steps, from as many as 4 or even 5 steps in pre-planned turns and as few as 2 or 3 in the late cued. Across these multiple turn strategies and across pre-planned and late queue turns as well, we've preliminarily identified that the role of each foot's single stance phase remains the same regarding accomplishing the turn's mechanical objectives. So we observed that the foot inside of the turn, or the left foot for left turns, is more responsible for rotating the pelvis and changing the body's facing direction, while the outside foot, or the right foot for left turns, contributed more to redirect the body's linear velocity in the new direction of the turn. We're also investigating the relationship of the base of support context at times of angular momenta extrema. During turns, the frontal plane angular momenta increases to rotate the body above the center of mass into the turn, resulting in a leftward rotation over the left foot. In this example trial, the frontal plane angular momenta is displayed as the color of the center of mass trajectory. As the turn begins at the green dot, the frontal plane angular momenta is large and to the left, even while the center of mass remains to the left of the left foot. This situation is potentially the most dangerous to frontal plane balance, as there is no support surface to catch balance if it's lost to the left. While this may not be dangerous for the young adults in this study, in the future, we will examine balance impaired populations, starting with older adults, to assess whether and how they change their balance control strategies during turns. With that, we thank our research participants, research assistants, and funding. And at the end of this session, we're happy to take questions. Thank you.
Thank you, Mitchell. Okay, so we will move on to our next presenter, Ojun Zhang. You can go ahead and start sharing your screen. They're from Northwestern University, and they're presenting their research on prior exposure to environmental uncertainty may limit adaptation of predictive control strategies during a goal-directed walking task.
Yeah, thank you so much for the introduction. And hello, everyone. My name is Ojun Zhang. I'm excited to present results from my current study. The title of my talk is Prior Exposure to Environmental Uncertainty May Limit Adaptation of Predictive Control Strategy during a goal-directed walking task. Following neurological injury, Gait rehabilitation aims to help patients form an accurate internal model to control consistent aspects of their working environment. Gait rehabilitation also aims to help patients improve their ability to manage external uncertainty in order to handle variable real-world challenges. However, the effect of introducing uncertainty on locomotor adaptation is not known. We are particularly interested in how and when one should begin in incorporate uncertainty, or in other words, reactive type practice into a gait training intervention. We performed the following experiment to investigate this problem. The participant wore a snug harness around their waist and attached bilaterally to a cable-driven robot used to apply laterally directed forces of varying magnitude. 3 types of forces were applied to the participant. No forces were applied in the non-field. Pseudorandom perturbations were impulsive lateral forces applied to the participant that had unknown lateral directions, magnitude, and frequency. Finally, in the consistent viscous force field, the lateral forces applied were proportional to participants' forward velocity. We call this field a consistent viscous force field since the gain between forward velocity and applied lateral forces were a constant. 26 healthy young adults were assigned to one of 2 groups. Both the perturbation group and control group experienced the identical series of walking trials, starting with 20 non-field baseline trials and ending with 70 consistent viscous force field trial. However, there was one exception. 30 pseudorandom lateral perturbation trials were included before the consistent viscous force field for the perturbation group. In addition, we defined the first and the last 4 trials of consistent viscous force field trials as the early field and late field, respectively. Both groups of participants adapt to the viscous force field. The first video shows the baseline. In the baseline, In the non-field trial, the participant walked a pretty strict trajectory, just as their normal walking. And during the early field, the first 4 trials in the consistent viscous force field, the participants show a significant deviation to the right, the direction of the applied forces field. During the late field, the last 4 trials in the consistent viscous force field, the participants reduced their lateral deviation to the right compared with the early field. To quantify the movement error, we established a metric, what we call their center of mass sign deviation. This is the sign area of the center of mass trajectory relative to a straight line path originating from the lateral center of mass position at the first toe off and ending with the center of mass position at the rest within the end target. Both groups were able to adapt to the consistent viscous force field and showed a decreased movement error with practicing. In contrast to the control group, the center of mass trajectory and center of mass sign deviation of perturbation group did not return to the baseline at the late field. This observation suggests that the prior exposure to environmental uncertainty impedes locomotor adaptation to novel and consistent aspect of the external environment. The primary outcome of my study was that prior exposure to environmental uncertainty limited adaptation of predictive control strategy during a goal-directed working task. Thanks for listening. I welcome your questions.
Thank you very much. So we'll move on to our next speaker, Gabriella Small from the University of Texas at Austin. If you want to go ahead and start sharing your screen. They will be presenting their research on the effect of cognitive load on balance recovery strategies used during walking.
Hi, thank you so much for that introduction. As she said, my name is Gabriella Small. I am a graduate student at the University of Texas at Austin. And today I'm going to give a brief talk on this dual task study. So in order to successfully perform activities and move around in your everyday life, you have to maintain control of your balance. Dual task studies often combine steady state walking with an additional cognitive load to assess their influence on gait performance and balance. Our previous study found that when confronted with a challenging cognitive load while walking, young healthy adults actually prioritize and focus more on their cognitive performance at the expense of their balance control. We also know that foot placement plays a critical role in balance control, with any errors in foot placement leading to a loss of balance. But how dual tasks influence the response to foot placement errors is still unclear. Therefore, the purpose of our study was to determine how an additional cognitive load would affect the balance recovery strategies used after a mediolateral perturbation to foot placement in young healthy adults. To achieve this, we had 15 healthy participants walk on a treadmill in a single task condition with no cognitive load, and 3 dual task conditions, which paired a cognitive load with walking. These were listening to a podcast, spelling short 5-letter words backwards, and then a really hard one, spelling 10-letter words backwards. Then while walking, we had a custom pneumatic device attached to their ankle that at random steps throughout the trial would perturb their foot. So essentially you're walking and right before heel strike, your foot is going to move and land somewhere you did not expect it to. To analyze the recovery mechanisms, we investigated the ankle inversion and hip abduction moments. So as you can see from these plots, all of the squares are grouped together and all of the triangles are grouped together. So that means cognitive load did not affect ankle or hip peak moments or when those peaks occurred during the gait cycle. And that's true for both the lateral perturbations, those are the squares on these plots, or the medial perturbations, those are the triangles. So individuals did not change the recovery strategy for each dual task. But we also wanted to know what happened to their cognitive performance? How fast and accurate were they able to spell during the perturbations? We found that cognitive performance decreased during the perturbed dual task condition compared to just steady state walking. So people's spelling ability got worse during the perturbed conditions. Now, at first glance, this might feel a little intuitive, right? Because I care more about not falling on my face than did I spell this word correctly. But if you put it into context with our previous study, it's actually really interesting because our previous study found that during steady state walking, people focused more on their cognitive load than on their balance control. But the second that there was a threat to their balance, in this case, the foot placement perturbation that we provided, people would switch and focus more on their balance and motor performance and less on their cognitive load. So that's why we do not see a change in the recovery strategy that people used. But we do see that the cognitive performance or their spelling ability decreases during the perturbations. So in conclusion, this research provides further insight into the automatic nature of walking in healthy young adults. And it creates the foundation for future studies in neurologically impaired populations, since it's still unclear how they would prioritize their cognition versus their balance, and are they at risk of falls for how they prioritize these things. And that's especially important as the current generations age with constant distractions and technology pulling at our attention while we walk. Lastly, I would like to thank my advisor, Dr. Neptune, and everyone in the Neuromuscular Biomechanics Lab for their help with this project. And thank you all so much for listening. I'd be happy to take questions at the end.
Very much, Gabrielle. So our next presenter and our last one for this session is Alka Bishnoi. You want to go ahead and start sharing your screen. She's from the University of Illinois at Urbana-Champaign. And we'll be presenting the research on effect of perturbation on brain activation and walking performance in older adults with and without osteoarthritis.
Hello, everyone. Thank you for the introduction, Sarah. So I will be presenting effect of perturbation on brain activation and walking performance in older women with and without osteoarthritis. I'm a final year PhD student at University of Illinois, and I will take the questions at the end, actually. So why this study? What is the motivation behind the study? So perturbations such as slipping and tripping, which happens during walking in older adults, can lead to falls and mobility impairment, and which further can lead to fall injuries, fear of falling, and which can further lead to gait and balance impairment in these adults. But since we know that older adults will be facing these kind of issues, is osteoarthritis can further exacerbate these conditions, or is it causing more impairment in these adults? So we also wanted to see if these conditions has an effect on brain activation and walking performance of these adults. So objective of our study was to explore the differences in brain activation during walking perturbations in older women with and without OA. And we also wanted to see if there will be any changes in walking performance before and after perturbation. We hypothesized that there will be increase in prefrontal cortical activation, which we define as brain activation in our study, which I will go more in detail, during the perturbation task and related to walking tasks, which means that they had to use more attention resources to do the same task, which they can do with less attention resources during the normal walking. And there will be differences in the PFC activation among the cohorts, which is your OA with osteoarthritis and without OA, HOA, healthy older adults, basically. And we also wanted to see that there will be changes in walking performance. So we are saying that after the perturbation task, there will be changes in walking performance, such as stride time, stance time, stride length, and stride width. So we recruited 9 older women with osteoarthritis and 11 older women without osteoarthritis. In our study, we find their predefined comfortable speed on the instrumented treadmill, and they were supposed to do 2 normal walking trials, which we defined as N1 and N2, and 2 perturbation trials, which were P1 and P2. while wearing the functional near-infrared spectroscopy headband, which will measure their prefrontal cortical activation, which looks something like this on the right-hand side on the picture. So they are wearing this headband, which measures their oxygenated hemoglobin and deoxygenated hemoglobin. It's something similar to the fMRI that you see, and the levels that you see for the oxygenated hemoglobin, which is red in color, and for deoxygenated hemoglobin, it's blue in color. This is the normal process, like mostly during the walking or any activity, the oxygenated hemoglobin will rise up and deoxygenated hemoglobin will go down. That means there is an increase in PFC activation. And this was recorded during their walking trials. So this was, the order of trials was N1, the normal walking, then there was the first perturbation P1, then the second perturbation P2, and then the normal walking 2. Each perturbation trial was of 2 minutes and had a pseudo-randomized 10 slips, which were intervened between 2 to 25 seconds. So they were unaware of when the perturbation will be coming, and they got the time to best recover themselves as well before the next perturbation. We recorded their stride length, stride time, stride width, and stance time, which this data was extracted from the instrumental treadmill. And we also found interesting things, that there was differences in the age of these cohorts. There were differences in the normal walking gait speed. And this gait speed is when they are overground walking. And this was also significantly different between these cohorts. The WOMAC pain score is the osteoarthritis pain score level, which was obviously significantly different between these cohorts because we are taking osteoarthritis and healthy adults, so they will show differences in the pain score. Also, there was difference in the body mass index. So we used these as the covariates in our study, and we wanted to see if after controlling these covariates, are we still seeing the PFC activation level differences in these cohorts or not? So with our linear mixed model analysis, we found PFC activation levels increased during the perturbation task relative to walking task, which says that our hypothesis was correct. And we found these changes in both the cohorts, even after controlling for the covariates. And we also saw the interaction between the cohort and the task. As you can see from the table as well, there was interaction between cohort and task for both the HbO2 and HB. And which says that there is a difference in between the cohorts or not. So further, we wanted to see by the post-hoc analysis if there is a difference between the cohorts or not. But we didn't find any PFC activation differences between the cohorts, but we did find overall changes between the tasks. In terms of the changes in walking performance, we found stride time, stance time, and stride length increased significantly going from the normal walking first trial to the last normal walking trial. So the 2 perturbation trials had an effect on the walking performance basically, but we didn't saw any change in the stride width. So what's the point of all this? What are we saying? So we are saying basically this is, first of all, that these 2 perturbation trials can lead to increase in PFC activation. So a short bout of perturbation trial can lead to increased brain activation and walking performance in older adults. And this can further explained by the changes in the walking performance after perturbation. So there is the importance of using perturbation training in rehabilitation protocols in older adults with and without osteoarthritis. So this is the final message. And thank you, everyone. I will take the questions now.
Thank you very much, Alka. So now we're going to open up to questions, and I'll hand it over to Jeremy.
All right, great. And I want to applaud the audience too. You've made my job busy, so I appreciate that. We will start with Mitchell Tillman. And I encourage you and Satya to please meet up in the spatial chat. There's a few questions. I'll try to summarize part of it here. A very nice talk. Very interesting that the late cued turns are executed with fewer steps. Is this a consistent finding? And any thought about why?
Yeah, thank you for the question. It was a consistent finding that the late cued turns had fewer steps than the pre-planned. And I would guess that that's because we define the turn phase by pelvis angle. And so in the late queued, there was less anticipation or less pre-rotation, I'll say, of the pelvis, and therefore the pelvis onset of rotation happened later, and it occurred over a shorter time period.
Wonderful. The next question is for Asian. There was a couple questions that kind of were in the area of thinking of short versus long-term effects and the role of the washout period. So I'll highlight a question from Anne Elizabeth Martin. Do you think you would see the same results if you included a no perturbation washout period between the random and constant perturbations?
Yeah, thank you so much for the question. I think a washout period between random perturbation and consistent viscous force field may help alleviate the effect of random perturbation. However, in my study, perturbation group did not return to the baseline even after 70 trials of training, in my study, more than 20 minutes walking. So I think the random perturbation has a pretty long-lasting effect on the subsequent training.
Thank you. All right, we will move on to a question for Gabriella. And Gabriella, you should know that you had a very productive question period, so I encourage you to save the chat, and hopefully things can continue. And I apologize, I can't get to everyone's question. We'll go with a question from Younghee Chang. Neat results. There was no change in peak moments, but did you see any changes in the timing of the joint moment responses, or the delays in the start times or the peaks?
Yeah, that's a great question. So we also didn't see timing in joint moment peaks or like when the reaction started in the different dual task conditions compared to steady state. They were all the same.
Great. And we'll move now to Alka. And I apologize if I'm not getting some of these last questions down, and I haven't really curated these. So we will go with a brief question from Ajit Chadari. Alka, nice work. Can you talk about the importance of this being in prefrontal cortex? Does this mean increased focus or attention on the task?
Yeah, that's a very interesting point. I forgot to mention during the presentation. So the point of using prefrontal cortex was actually to see if they had to use more attention or for the task when they're walking, or is perturbation seems like in addition of the task with the walking. So we wanted to see that. And usually prefrontal cortex and executive function and increased focus and attention, these terminologies are usually used for the dual task walking paradigms, or if we want to induce something cognitive load with the walking. But this is the first time we are using with the perturbation. So we wanted to see if there is a kind of a pain mechanism which is taking into place in with the cognitive control in people with osteoarthritis. So if walking was very difficult for them to use the increased attention resources in their prefrontal cortex to do the same task, which healthy adults can do with less attention resources or none at all. I hope I answer your question.
All right, if not, again, really pushing the spatial chat for some good engagement here. We have a couple minutes. I'll try to highlight some other questions. Going back to Asian, this question is from Brian Selgrade. Nice talk. It looks like your videos that the trials were overground walking over 3 to 4 steps total. Do you think you'd see similar results if the perturbation were applied during continuous gait without the effects of gait initiation or termination?
Yeah, thanks for the question. And in my study, we defined we designed our final target is about 2 steps away from their starting location. And I think this question is pretty good. And we actually did some analysis for the first step, and we did find some significant difference between 2 groups in the first step. They have the perturbation group has significant lower lateral velocity during the first step, and I think the result will be a little bit different if we perform this study in the setting of continuous walking. Thank you.
All right, on that note, thank you. We've apparently run a really tight ship here and we're ending on time. So I want to thank my co-moderators, Antonia and Sarah. Thank you to the speakers, outstanding presentations. Thank you for our audience for being so engaged. For the speakers, I do encourage you to save the chat. I'll try to do the same myself. And let's move this conversation to Spatial Chat. Room S2 Mary, maybe we can get that link on the chat as well. Otherwise, thank you and enjoy the rest of your conference.
Thank you to the moderators.
Thank you, everyone. Appreciate it.
Thank you, everyone.